Okay, let's go ahead and move on to page 5. This is kind of a fun little exercise. And you've seen these, I'm sure, in Alex. If you haven't, they'll be coming up soon. So describe how the rate of change of a linear function relates to the behavior of the graphs below. So on number 1, identify the graph that best represents the distance traveled by a car driving at a constant speed. So take your pick. I'll give you a second. So I will tell you a lot of students pick A, but if you remember back to the parking lot problem, at time 1, they're this distance from home. At time 2, they're the same distance from home. At time 3, they're the same distance from home. This is not a constant rate. This is a parked car. The distance from home is not, so remember this was home. The distance from home is not changing. They're staying in the same spot. So this would be a parked car. So this is definitely not it, since the distance is not increasing. This one, at time 1, they're this far from home. At time 2, they're further from home. At time 3, even further. Remember how we said lines have a constant rate of change? Constant speed. So this is the one. And the reason C isn't is because they're stopped, and then they're accelerating slowly, and then moving on. So this would be more like a car at a stop sign. So it's not a constant speed because they're going slow, and then faster. So this would be a car leaving a stop sign, or, leaving your driveway, where it's a slow rate of acceleration. Sign. And definitely not a constant speed, slower and then fast. So a car leaving a stop sign would be an example of that. Okay, number 2, identify the graph that best represents the speed of a car coming to a stop. So the speed of a car coming to a stop. So which one do you think? Did you say A? Because the car is going to gradually slow down and stop. So A it is. This would be a car that is parked and then time stopped. Not possible. So you could say the speed was 45, 45, 45, 45, and then it came to an abrupt stop. So maybe this is the car hit a wall. So constant speed. So the speed doesn't change. So 35 miles an hour, 35 miles an hour, 35 miles an hour, 35 miles an hour, 0. Well, we can't go 35 to 0 in the same instant. So this would be like a car hitting a wall. Where it's going a constant speed and then all of a sudden it stops. That's not how we stop our cars, and we can't stop that fast unless something helps us. This I like to call the California stop. Slow down, slow down, slow down. Don't quite hit 0 and then speed back up. So this is definitely not a stop because speed would have to be 0. Here, speed is 0. That's how we know this one stopped. But this one, the speed is never 0, so it's not stopping. So this is a California stop. Just kind of roll through the stop sign or stoplight or whatever it is. Maybe the light, they're slowing down and then the light turned green and then they're accelerating. But if you're at a stop sign, it would definitely be a California stop. This is only one that is accurate because the speed is 0 and it gradually becomes 0. It doesn't instantly become 0. Identify the graph that best represents the height of an arrow that has been shot straight up and lands on the ground. So you have to take into effect gravity. So nothing goes up and makes a right turn and comes down. What this one makes me think of is someone standing up in a classroom and they throw a pencil to hit the ceiling and the pencil bounces right back down. That would be a case where it would make a right turn because it goes up, it hits the ceiling, comes back down. So this one definitely not. Pencil hitting a ceiling. Where it hits, it turns around and comes right back down. Not an arrow shot in the air. And I have a lot of students that'll pick this one, but there's no time passage. How can anything happen without time passing? We're at, let's say, 2 seconds. At 2 seconds, nothing can happen. The arrow can't go up and come back down in 2 seconds or in 0 seconds. So no time has passed here. This is an impossible graph. Time has to pass for something to happen. And this one, no time has passed. They're stuck on that. So no passage of time. That cannot be possible. Whoops, not on time, of time. And this one is the usual trajectory. You'll learn in 120, if you're going that route, that this is called a parabola. So if you hit a golf ball, throw an arrow, throw a football, this is the normal trajectory because of gravity. So here you are, you shot it up, it comes down and makes kind of a U-shaped, a parabolic shape, and then it hits the ground. So this would be the one. So kicking a football, throwing a football, hitting a golf ball, throwing an arrow, those would all be examples of a parabolic curve. Okay, so look over 4. Shut the video off maybe for 30 seconds. Look over it and see if you can pick which one you think would be a Ferris wheel. So this is the time elapsed, and this is the distance. What does that say? Distance from ground, I think. Maybe. I don't know. That's pretty shaky. Distance from ground. I think that's what it says. Yeah. So how high you are, in other words. Okay. So problem here. We're going out here and then we're going back in time. We can't travel backwards in time. So we went out to 3 seconds and now we're going back to 1 second. Not possible. So cannot go back in time. So what about this one? The Ferris wheel goes up, it comes down, not quite to the ground. It goes up, comes down. That looks pretty probable, don't you think? So we'll circle that as a possibility. This one, the reason this one doesn't work is because the Ferris wheel always comes back up to the same height. So when it's rolling around, it goes up to that height, then it goes back down to the ground, then up to that same height, back down to the ground. This one doesn't. This would be more like a roller coaster. If you were going up the hill, down, up a smaller hill. So definitely not a Ferris wheel, because the Ferris wheel has to go up to the same height every time. So when you're on top of the Ferris wheel, you're at the same height both times, not at different heights each time. And this one again is back in time. We can't go out to 5 seconds and then go back to 2 seconds. So cannot go back in time on that one. So that is a fun little exercise. Okay, let's look at the next page. This should be familiar. This is a review of what we learned in Module 6, and then we talked about again in Module 7. So I like this. This is a good one. My dog is snoring, so I'm going to get her out. So go ahead and look and see if you can do 5A and 5B. Sometimes I forget to put her out. Sorry about that. Okay, so the slope. So we have to do rise over run. So let's write that right here. Rise over run. So we're rising. Remember, we always start at the left-hand point. Rising, what is it, 25? Because it's right in the middle. So I would say we're rising 25 and running 5. So 25 over 5. So rise is always in the numerator, run is in the denominator. So rise over 1, run 25 over 5, which is 5. Then we're going to practice writing the equation of a line. We did this back in Module 6, so it's been a little bit. So now we have to take our y equals mx plus b, and we did them earlier in our notes too with the word problems. So we know m. B, remember, is the y-intercept. So if you need to write that to remind yourself. So this is the slope, whatever's in front of the x. This is the y-intercept, just the y-coordinate. So we have y equals 5x plus, what's the y-intercept? Where does the line cross the y-axis? 0. So now that you've seen one done, I would shut this off. These are all on your test coming up. So this is really good stuff to make sure you know how to do. So I would shut the video off and do those next 5 and then come back and we'll compare answers. Okay, so slope on this one, it looks like we're going by 1. So rise 1, 2, 3, run 1, 2, 3. So it's looking like 3 over 3. And if you're not sure that's right, try another one. Rise 1, 2, 3. Run 1, 2, 3. So you can see it is indeed 3 over 3, which is 1. So rise over run equals 3 over 3, but we always have to simplify it, so slope is 1. So we know our m is 1. Now we have to figure out b. Let's just write it here. M is 1, b is, and b's where it crosses the y-axis. So that looks like -7, 8, 9, 10, yep, -7. That's where it crosses the y-axis, because that's what b is, the starting point, if you were just looking at this. So the starting point's -7, and it goes on forever. So that's where it crosses the y-axis. So going into y equals mx plus b, it'd be y equals 1x minus 7. Or even better way to write y equals x minus 7. That's a little more grown up. But if I was graphing it, I would keep the 1 in it. I would even make it 1 over 1. But if we're just writing the equation of a line, we generally don't put the 1s in. I tell Alex not to count it wrong if you put it in, but in other classes, they're not going to want it there. So I would just practice writing x, because 1x and x are the same thing. Okay, so rise over run. I see this line is falling. Whenever a line is falling, that tells me my slope is going to be negative. So I'm going to put my negative there to remind myself. So down 1, 2, 3, 4. Let's write it right here. I think we're going to have to finish this one. after the video stops because we're running out of time. So let's put the -4 there and then we'll pick up.